Hello everyone, welcome to YouTube channel Energy-Exergy Theory Applications. I am Professor Morosuk and I am the author of this YouTube channel. Today we are with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel and share the link with your colleagues. Exergy analysis part 2. Today we will revise some information that already was discussed in the first part of this lecture, and also we will go deeper with the equations that already were written in a general form, and we will proceed already with some applications for the components. Let us repeat that thanks to exergy analysis, we can identify location, magnitude, and the causes of thermodynamic inefficiencies within energy conversion system. We can apply exergy analysis on the component level, but also we can apply exergy analysis on the level of energy conversion system, regardless how complex is energy conversion system. And very important that inefficiencies will be associated for us with the value of exergy destruction, which describe the irreversibilities within the system, and the term of exergy losses, which means exergy transfer to the environment. I would like to repeat this. It is not exergy transfer from one system to another system. It is exergy transfer to the environment. And let us redraw the schematic of energy conversion system for the exergy analysis as multiple exergy streams are coming to the system and multiple exergy streams going out from the system. So some of these streams, of course, it is exergy streams associated with heat interactions of system with sorting, some of things with work interaction, and also can be material streams coming and going out from the system. So at present for us, we will deal only with exergy streams coming in and going out. The difference, as we already know, it is the term of exergy destruction associated with irreversibilities, and also we have the term exergy losses that we just discussed. Exergy losses can be associated with one of outgoing streams or maybe with several outgoing streams, and this we need to investigate. The old version of the exergy analysis, when exergy analysis was just developed, it was approach exergy in, exergy out. So exactly what I just discussed, that exergy streams coming to the system and exergy streams going out from the system. And for the components, when exergy analysis is applied on the component level, we can use the approach that exergy losses within the component will be charged to exergy destruction for simplification of analysis, and term of exergy losses will be vanished from this equation. But we will not lose the information, because in this way exergy destruction, term of the exergy destruction, it will be higher than the only irreversibilities. Also losses will be charged to exergy destruction. And exergetic efficiency, if exergetic term of exergetic efficiency, if it will be calculated using the approach exergy in, exergy out, then that will be an appropriate definition, because it will, we know this definition out divided by in contradict to the definition of performance, general definition. Therefore, we in the modern exergy analysis, we are moving from the concept exergy in, exergy out, to the concept of exergy of fuel and exergy of the product. In this way, exergy of fuel and exergy of product, it is the already cumulative streams. So we have only one stream exergy of fuel, one stream exergy of product, but in fact it can be many contributors to form these two cumulative streams. Does not matter, we will apply concept in out or concept fuel and product, the term of exergy destruction for the system and exergy destruction for the component. Anyway, it will be the same value. So that's why we will not get different results related to irreversibilities exergy destruction, but with the concept of fuel and product, we can properly calculate efficiency, exergetic efficiency, which is exergy of product divided by exergy of fuel, regardless if it is exergetic efficiency of the entire system or if it is exergetic efficiency of the component. And this is the strength of modern exergetic analysis, that we can properly calculate and discuss further, calculate exergetic efficiency and discuss further how to proceed with improvement of components and, of course, of the overall system. So now let us a little bit more focus on the balances, how to deal with the balances, because usually it is challenging for the students how to start to write balances. I always propose you to start with the evaluation of the entire system, because it can be the case that you don't need to proceed with the evaluation of components. It is sufficient for some reason to evaluate overall system. Then, of course, for the simulation, we have streams coming to the system and going out from the system, and we can calculate exergy destruction as in minus out, as we discussed it before. And as you can see, exergy losses are, I put especially in parentheses, because maybe exergy losses are already one of the exiting streams. This is very important, that we will not count it twice, our outgoing streams and plus exergy losses, because maybe one of these three streams will be associated with the exergy losses. So we can also proceed with the evaluation of exergy conversion system using the concept of exergy of fuel and exergy of product. And definitely the value of exergy destruction, regardless of the approach, will be the same value. Therefore, if we would like to calculate exergy destruction of the entire system, then proper definition will be exergy of fuel minus exergy of product minus exergy of losses. So means that exergy of fuel, exergy of product, exergy of losses should be defined, because these three terms associated with exergy transfer through the system boundary, and we can control all the streams. And exergy destruction, it is the last term that always should be calculated through balance. This is very important. But how can you prove that the value of exergy destruction calculated properly? Then we have only one possibility. We need to conduct exergetic analysis on the component level, and the term of exergy destruction within the system, it is the sum of exergy destruction within all components of the system. Only like that. And usually we always need to conduct to calculate exergy destruction, for example, for each component, and after that sum to check with the total balance of the system. So we always should check both values, and if they're the same, of course, analysis applied properly, and we can proceed already with evaluation. So now we return it again with the questions how to evaluate components. And we already several times repeat these questions, and nevertheless, I will again use them, but now only two. Which variable characterize the thermodynamic performance of a component? And we know that it is exergetic efficiency of the component. Which variable should be used to compare the performance of similar components in the same system? Or we can also use different components in different systems. So it is exergetic efficiency. Now, example. Let's assume that we have three components within the system. Component A, component B, component C. I especially use different shapes for these blocks to demonstrate that these components are different. And according to exergy analysis, we applied properly exergetic balances, and we found out that exergy destruction within each of these components absolute the same. Exergy destruction within component A, 10 kilowatts, within component B, 10 kilowatts, and within component C, also 10 kilowatts. How to proceed with improving of the system? Which component should be improved? So I repeat that the value of exergy destruction we can also calculate using the principle of entropy generation, and we will also will obtain the same information. So now exergetic analysis in the term of exergy of fuel, exergy of product. We calculated that for the component A, exergy of fuel 11 kilowatt, exergy of product 1 kilowatt, therefore exergetic efficiency of component A is 9%. For component B, we have different value for exergy of fuel and exergy of product that will end with exergetic efficiency of 90%. And for component C, exergetic efficiency will be 99%. Usually, values of exergy of fuel and exergy of product we will not include to the evaluation. We have only two values to discuss: exergetic efficiency and exergy destruction. So now we can see that we have three components with the same value of exergy destruction, but with completely different values of exergetic efficiency. Now the question: which component should be improved? Of course, component A, because exergetic efficiency is only 9%. Sometimes people are asking, can we improve component B, for example, or component C? Because exergetic efficiency is quite high, 90% or 99%. Do we have mechanism to improve these components? Yes, we can. Not always, but we have such a mechanism. And mechanism is associated with reducing of mass flow rate through the component. Because if we will discuss about decreasing of irreversibilities, definitely it's difficult to do something with component C. It's already 99%. It's almost impossible to improve this component. But if we will decrease mass flow rate, so we will do not component optimization, we will have structure optimization, then this value can be reduced and component will be improved. Not only this component, maybe other components also. So these particular cases we will discuss with different application. So now if we are applying a modern version of exergetic analysis, means concept of exergy of fuel and exergy of product, we can find out that there are two types of components. It is productive components and dissipative components. What it means from the exergetic point of view, from the analysis point of view. For the productive component, we have definition of fuel, we have definition of product, and we have exergetic efficiency as product divided by fuel. For the dissipative components, we have no fuel and product. Exergy is destroyed within this component, and we have no positive exergetic effect because of using of this component within the energy conversion system. Therefore, for dissipative components, no exergetic efficiency is calculated, only the value of exergy destruction. And then no need, since no fuel, no, we easily can calculate exergy destruction as a difference between exergy in, exergy out. But the value of exergy destruction ratio, we have these two equations, regardless it is productive component or dissipative component, these two variables can be calculated and of course will be included to the evaluation of component and of the system. Now we will discuss productive components. For productive components, we need to define what means exergy of fuel and what means exergy of product, exergetic fuel and exergetic product. Let us assume that we have a component which is productive. We have several streams coming, exergy streams coming to the component and several streams going out from the component. Now, how to find out which stream is fuel, which stream is product, and how easily to define fuel and product. We have official definition exergy of fuel, particularly here on this slide is given exergy of fuel. It is possible to follow this definition, but believe me, quite difficult to apply this definition, particularly when you have a complex component with many streams. I will give you a very simple explanation what means fuel. If we have a component, we need to consider each stream, each material stream or energy stream that is going through the component. If we found out that for this stream, exergy at inlet is higher than exergy of outlet, it means that exergy is moving from this stream to other stream, with other streams, better to say, because we don't know how many of them, within the component. So this exergy stream supplies exergy to other streams. It means that this stream is assigned to be fuel. And we can already see that fuel, it is not only incoming stream, it is the difference between exergy of the same material stream or energy stream, incoming minus outgoing. This will be the fuel. There is an interesting case. For example, a stream is only coming to the component and after that disappearing. This is the case that theoretically difficult to understand, but practically very simple. It is work supplied to the component. We supply work, and of course, after that, no stream of work going out from the component. Then in is also higher than out because out is equal 0. So such streams also assigned to be streams of exergy of fuel. Now with the product. Again, we have a component and we have one material stream. And we found out that exergy at the inlet of stream is lower than exergy at the outlet of the stream. It means that exergy supplied to this stream within the component. It means that this stream associated with the product, because idea of component to increase exergy for one or several streams. Absolute the same, we can find out that there is no incoming stream, but there is only outgoing stream. Example, work is produced within the component. Then incoming exergy 0, because the stream does not exist as incoming, but exists as outgoing. This also will be the stream associated with the exergy of the product. Now, let us give several very simple examples just to show the application of the theory. Much more complex examples we will discuss within other lectures. Let us assume that we have compressor that operates fully at temperature higher than environmental temperature. So we know that compressor is a productive component. We have productive component, and we need to identify which streams are coming to the component and going out of the component, and what is the fuel and what is the product, I mean exergy of fuel and exergy of product of the compressor. What is the goal of the compressor? It is the compression stream from state 1 to state 2. Please always remember, it is not from the environment to state 2. It is from state 1 to state 2. Therefore, we have one stream. It is material stream. It can be any working fluids going through the component and compress it from state 1 to state 2. And for the compression process, for compressor, work is supplied. Only supplied. So full work will be supplied to the component and there is no outgoing stream associated with work. Used previous discussions. Stream 1, 2, it is the product because exergy is increased. At the end of compressor, we have temperature higher than inlet temperature and pressure is higher than inlet. So exergy is increased, means that it is the product and work is supplied and there is no stream going from the component associated with work. So work, it is the fuel for the compressor. And the definition, product for the exergy of product for the compressor, exergy at stream 2 minus exergy at stream 1, the difference, and fuel of the compressor associated with the work of compressor. I repeat, this is the case when compressor operates at temperature higher than environment. Now, a little bit faster discussion about turbine. Also, we assume that turbine operates at the temperature and pressure higher than environmental. The idea of turbine is to produce work using the expansion of working fluid from state 1 to state 2. So it means that a working fluid is going through the turbine and exergy is subtracted from this stream. Inlet, exergy at inlet higher than exergy outlet. Means fuel of the turbine, it is exergy inlet minus exergy outlet. And work is produced. So it means that this is stream going from the component and there is no incoming stream of work. In conclusion, product of the turbine, it associates only with exergy of product, associates only with work produced by turbine, and fuel, it is the difference between exergy at inlet and exergy outlet. and heat exchanger. Again, the simplest case, two-stream heat exchanger that operates above temperature of the environment. We have hot stream and we have cold stream, and both streams are with temperature and pressure higher than environmental conditions. This is very important for us because when we are higher than environment, we should remember that the higher temperature, the higher exergy. So one stream, hot stream, at inlet exergy, stream 3, is higher than outlet, stream 4. Therefore, this stream associates with the fuel, and exergy of stream 1 is lower than exergy of stream 2 because this stream should be heated. It is the product. Finally, we have the definition for the heat exchanger that operates at temperature higher than the environment. Fuel, it is the difference at exergy, at the inlet outlet for hot stream, and product, it is the difference between outlet and inlet for cold stream. And now we are with the dissipative components. Which components are assigned to be dissipative? Dissipative components, this is component mainly associated to the, I will repeat again the word component, to make a cycle closet, or for some purposes. For example, to decrease pressure for some streams. You know, for some operation conditions, we need to decrease pressure to given conditions, but we will only lose exergy because through decreasing of pressure, we will not gain anything positive. Or, for example, we have heat transfer to the environment within condenser and exergy transfer to the environment. Or we have intercoolers between compressors. All these components are assigned to be dissipative. So we need these components for energy conversion system. We cannot remove these components because we need for the realization of the cycle of the entire process. But from exergetic point of view, this is dissipative components. And I repeat, for dissipative components, exergy destruction, it is exergy inlet minus outlet, and no exergetic efficiency should be defined. And examples. Throttling valve, it is a classical dissipative component only if throttling valve operates above of the environment, means for power generation system. Throttling valve for the refrigeration system is a productive component. This particular case we will discuss later. I repeat, throttling valve is a dissipative component only for the system that operates at temperature and pressure higher than the environment. For example, mixer. Any kind of mixers are dissipative components. Which kind of mixers can be? We can mix, for example, the same material stream with the same pressure but different temperature. Or the same temperature, different pressure. Or both temperature and pressure will be different. Or it can be temperature, pressure, and even material of the stream also will be different. We will only destroy exergy and we will not bring any benefits to the system. And in the previous versions of exergy analysis, maybe you can find the definition that mixer is this productive component, but in the latest version, we decided that mixer is a dissipative component, simply because we need mixers, but we cannot improve mixer itself. The same, we cannot improve throttling valve itself. And I already mentioned dissipative components, also condensers and also interstage coolers. In this way, if we're writing inlet minus outlet, it is assigned to the streams for the cycle 1 minus 2, 1 minus 2. In this way, streams 3, 4, it is exergy transfer to the environment, we just vanished from the analysis and we even don't need to simulate parameters in these streams. Next lecture, it will be exergy analysis part 3. We will continue with exergy analysis and with more and more applications. If you found this video and this information very useful and interesting for you, please give a like to this video, subscribe the channel, and share this link with your colleagues. Thank you.